Hello everyone, welcome back to the SWAM NPTEL course on engineering aspects of biofuels and biomass conversion technologies. I am Professor Ijaz Ahmed, currently Assistant Professor in the Department of Chemical Engineering at IIT ISM Dhanbad. In Module 5, Lecture 1, we already discussed about the biomass characterization for gasifier application. And as a whole soul in Module 5, we will be discussing about the large scale gasifiers. In lecture 2, particularly, we will discuss about large-scale gasifier theory and the process flow development. If you remember, in the previous class, we discussed about the ultimate and proximate analysis of the biomass. Particularly in proximate analysis, we learned about calculation of the moisture, volatile matter, ash content, and fixed carbon. And in moisture, what we do? We take the sample, heat it at 105 degrees Celsius until it becomes constant. Once it becomes constant, we take the wet biomass weight, which was the initial, and subtract the dry biomass weight and divide it by the original weight, and then we get the moisture content in it. Now, similarly, for example, we took the 10 gram of biomass, and after drying it became 8.5. So what we did? We did 10 minus 8.5 by 8.5, and we got 15% moisture. Okay. Similarly, we also learned that if we heat the biomass at let's say 195 degrees Celsius, we will get some weight. Okay, and that will be termed as the volatile matter content in the biomass. Now, usually what we do for volatile matter content is, let's say if you have weight before heating W1 and after heating you are getting W2 and you have to calculate the Vm percent, then what we will do, it's W1 minus W2 upon W1 into 100 to get in percent. So this is how we calculate the volatile matter. Similarly, for ash content, what we do, we burn the biomass at 750 degrees Celsius unless a constant weight is achieved. Now, once we have the constant weight, what we do is that if I have to find the ash percent, okay, and my original biomass, let's say, is something like, for dry biomass, I say I have something W dry, and then I have leftover W ash. So what I'll do is, it's W ash over weight of dry biomass into 100. I can calculate. Similarly, we learned how to calculate the fixed carbon. It's like from 100%, I will reduce the moisture content percentage. So this is in percent. Okay, percent, Vm percent, and ash percent, and whatever is left over is the fixed carbon. Now, with this background, let's discuss that, why large scale commercial gasifiers are important and how do we design them. And for this, as I told you in the beginning, that gasification is a high temperature process. Now, in this high temperature process, what happens is that we make gases, syngas from here, and syngas is used to produce the power, or we can use it to make fuel and chemicals. Now, to make fuel and chemicals, there are different processes. Like I told you, that we have usually Fischer-Tropsch process, by using which we can make methane, we can make C2C5 alkanes and paraffins, or C5 to C20 like transportation grade oil. Similarly, we can extend it from biomass to, in the feedstock side, we can extend it to coal, or we can extend it to natural gas, and we can do the gasification. Eventually, once we get the syngas, we can make a wide range of products. So I can say that large scale gasifiers are primarily not only required to generate the electricity, but the gaseous products that can be converted into a wide range of chemicals, as well as liquid fuels via Fischer-Tropsch synthesis. Now, this, as I said, like, it's not just the biomass that we can use. We can extend this process to coal, natural gas, and other raw materials, for example, municipal solid waste, or if any biomass waste we have, or any kind of waste we have that contains carbon and hydrogen into it. Now, from this, what we get is another part, electricity and synthetic chemical like diesel and kerosene, etc. Now, the question here is, when we already have learned that briquetting or pelletization is a good option to use the biomass as compared to the traditional usage or the conventional usage. So why are we concerned about the gasification? And for that, I'll say that let's say if we have a 1.5 meter cube of round wood, let's say some constant density, if we char it and we make the charcoal, which will be roughly around 120 to 140 kg, we'll get only 65 liter equivalent of the gasoline. While if we take this and we do the gasification here, the fuel that we get is equivalent to that of the 135 liter of gasoline. So you can see that it increases almost to double. Okay. Therefore, gasification is very important. We do it, what I can say, that increase the efficiency or overall utilization of the fuel value that we have. Now, uh, one example like I shared, so this is charring gives you equivalent to 65 liter of gasoline and gasification gives equivalent to 135 liter of gasoline. Now the question here is that how do we do that? So we have already discussed the preliminary theory of gasification in the previous, like when we discussed about the household gasifiers and the gasifier stoves. So it's a thermochemical process that transforms the biomass into combustible gases, particularly producer gas or CO2 rich syngas. Okay. Now these gases have a heating value around 10 to 1200 kilocalorie per Newton meter cube, and you can see that from 1 kg of dry biomass, typically we can get is 2.5 to 3 normal meter cube of the gas. Now this gas can be used, as I said, to make chemicals, or you can directly burn in the power plants to get the electricity, or we can make the transportation grade fuel, or we can do a lot of things. Okay. Now, as I said that with the charring, if I compare, like initially I said that charring gives around 35 liter equivalent of the gasoline, whereas the gasification gives the 135 liter equivalent of the gasoline. So I can say here that energy recovery in case of gasification is one of the most possible ways to recover compared to the briquetting and charring, and of course that makes it superior to the charring. Okay. Now this example I have shown earlier and I have already discussed, but just to repeat, but the point here is then what is gasification? So if you remember in the beginning I said that if this is, let's say, carbon, and if I give it complete oxygen, it will convert to CO2, while plus it will give me heat. Okay. Now if I limit this oxygen to half, what it will give me is CO. Plus if there is any hydrogen, it will give me H2. Okay. So this is primarily what happens in gasification. So it's a kind of, I can say, partial oxidation that happens, and we already discussed that here is, let's say, your biomass, that and then there is a drying zone, there is oxidation zone, there is reduction zone, and there is pyrolysis zone as well. So if I say in nutshell that gasification converts the carbonaceous materials into the syngas. Okay. Now syngas consists of carbon monoxide, hydrogen, carbon dioxide, as well as methane and some impurities like water vapors and H2S, ammonia, tar, etc. Now this is unlike the combustion where we give the complete oxygen and it converts into CO2. Here what we give is the partial, and that partial oxygen is roughly around 30 to 40% of the stoichiometric air required. This we have discussed already, but we will discuss here. So as I said that what happens during the gasification, that there are different zones where the biomass is treated. For example, the first zone is drying. Okay. Now in this drying zone, this operates around 100 to 200 degrees Celsius. So whatever biomass we are feeding, that undergoes drying to remove the moisture content, etc. Okay. And because moisture is evaporated, no chemical reaction happens, because the temperature range you see, this is quite less. This is almost 100 to 200 degrees Celsius. So herein the temperature is very less. Okay. Therefore, no chemical reaction happens. So this is a typical reaction. You see wet biomass, heat is given, we get the dry biomass plus H2O goes as vapor. Now then we come to this, once the biomass is dried, we have pyrolysis zone. Now pyrolysis zone operates around 200 to 600 degrees Celsius. Now this 600 degrees Celsius, the temperature is high. So, and biomass, as you know, I told you that it's a polymer of lignin, cellulose and hemicellulose. When we'll increase the temperature, there is likely to be a degradation of these polymeric materials. When they will degrade, they will form the smaller molecules. Okay. So what happens in pyrolysis zone, that the biomass decomposes into char, gases and vapors as well as tar in the absence of oxygen. That has to be noted here, because pyrolysis simply means that it is happening in the absence of air. Okay. Now, this is a complex process. As I said, it involves the depolymerization, and because cellulose, hemicellulose, lignin structure itself is very complex and varies from the biomass to biomass depending on the source, defining an exact mechanism is very challenging task. But in nutshell, we can say that when biomass is given high heat in the form of high temperature around 600 degrees Celsius, it usually converts to char, volatile and tar. Okay. Now depending on temperature, the amount of char, volatile or tar can be lesser or higher. Post this, it goes into the combustion zone, or we also call it oxidation zone. Okay. So it's partial combustion. Now this zone is at further high temperature around 800 to 1200 degrees Celsius. So now when we are giving oxygen here, you can see what will happen. The CO will form or CO2 will form. So in this zone, what happens? We give a controlled amount of oxygen or air or steam, whatever gasifying agent we are using, to the gasifying unit. Okay. And there it's like it's an exothermic reaction, so it supplies heat to the system itself. And the major reaction that we can see here is that, as I said, because I am giving here, you see this is the combustion zone, so I am giving the gasification agent. Let's say it is whatever it is, it will have oxygen, whether it's oxygen, air or steam, all will have oxygen. So if carbon gets the sufficient amount of oxygen, it will form CO2. Okay, that's again a exothermic reaction. It will release the heat. Similarly, if the limited oxygen is available to the carbon, which of course to all carbon complete stoichiometry will not be available, because I told you what we give is 30 to 40% oxygen we are supplying of a stoichiometric requirement. Okay, so here there will be incomplete supply, and that will lead to the formation of CO, which is again a exothermic reaction. Now from this, all these vapors, chars will travel to the reduction zone, and reduction zone is again it's 700 to 1000 degrees Celsius. So here what happens, the char will react with the gasifying agent to form the syngas. Okay. Now it's a like endothermic reaction, because the syngas has to be formed, and primarily the reaction that happens is, the first one is very common, is the Boudard reaction. So carbon reacts with CO2 to yield 2 carbon monoxide. Similarly, water gas shift reaction will happen to give carbon monoxide and H2, which is, this combinedly is referred as syngas. There is a possibility of, again, that the water gas shift reaction can happen with the CO plus H2O, and we can get CO2 plus H2. And then methanation reaction, where carbon can react with this H2 to form methane. Now these are all reactions which happens in the reduction zone. So we can say that in our gasification reactor, one of the most important reactions is, the zones is the reduction zone. Okay, where most of the desired reaction happen to get the combustible products. Now, as I said, the end product primarily contains around 15 to 25% of carbon monoxide, around 10 to 20% of hydrogen. This is a, lump sum value I am giving you. Again, it depends how the process has been optimized. Depending on that, these quantities may vary significantly. Okay, we can get methane around 1 to 5%. We get carbon dioxide around 10 to 15%. Water vapor depends on the, again, the gasifying agent we are using, first thing. Like we are using steam or we are using oxygen or air, the second, how much moisture content is there, and then what sort of composition is this. Depending on that, we can see what will be. And then nitrogen, if we are using air as a input, so nitrogen will be around 50%. Okay, so this is a typical composition. Now, because nitrogen is a non-combustible gas. Okay, so what happens? It reduces the overall calorific value of the gas because 50% of the volume of gas is occupied by the nitrogen. Okay, so one possible solution can be, instead of using air, we can use pure oxygen, and that will help us to get a high calorific value synthase. Similarly, if we look at the primary products of gasification are, I mean the combustible, which I can say, the carbon monoxide, hydrogen and methane, whereas the non-combustible are CO2, H2O and N2. So more the quantity of this, more is the calorific value, more the quantity of CO2, N2 or H2O, less is the calorific value. Okay. So typically, based on that, if you see the lower heating value of air blown gasifier, that means where we are using air as a gasifying agent, 4 to 6 megajoule per nm cube of LSV we get. Okay. If we replace air with oxygen or steam, the calorific value increases to almost 2 to 2.5 times, that is 10 to 14 megajoule per nm cube. And the obvious reason I told you, that when you get syngas from this, it is only the mostly combustible products, mostly combustible, while here the syngas has around 40 to 50% N2. Now this is a non-combustible gas, so it will not contribute to the calorific value or heating value of the gas. Okay, so herein what we can see that it is always better to operate a gasifier with the steam or oxygen. However, this is a theoretical aspect. The operational challenges can be there, and that has to be worked out. Now, as I said, that how to develop, I mean, the gasifier or large scale gasifier particularly, and what kind of engineering is required besides the theory. So first thing, as we know, it's just you can see where I say always that when you have to design a plant, you have to be a good dreamer. If you can imagine things, you can become a very good plant design engineer or PNID developer or a process engineer. So you imagine that what we do in gasification. So in gasification, what we are doing, we gasify. So let's say if this is my gasifier, I need gasifier here, and I have drying, I have pyrolysis, it has to move. That means we need a feeder here. Now the temperature here is high, so some cases we may need a preheater here. Now the biomass usually contains, arrow should be this side. The biomass usually contains the impurities and moisture, though there should be dryer, there should be sizing, then there should be the storage if we need continuous, and then there should be supply chain management. Okay, on this side we get gas and char and liquid, so we should have a GLS, then we should have a, you can say, gas filtration unit, and then you have, and so and so, like this is how you design. So if I start making a process flow diagram for a gasifying unit, what is the first thing I'll do? I'll look into that my raw material, there should be a good storage for my raw material. Okay, so the first thing I'll put is a biomass collection and storage unit. Okay, so the step one in as I said in developing a gasifier process flow diagram is biomass feedstock selection, and then collection and storage to the unit. After that, once the biomass is that collected and stored, what you need? You need pre-treatment. Pre-treatment, when I say, or rather we can say pre-processing. So as I said, you need to size it, you need to dry it, you need to remove the sand, stone and the other non-biomass particles from it. So we make a fuel preparation unit. Now this preparation unit is not a single unit, it can have lot of other units as well. Okay. Now once you have made the fuel, let's say here is your gasifier, what you need? You need to transport it. Okay. So this is here, we will see that in the step 2, that is biomass preparation, what we do, the biomass undergoes several pre-treatment steps that includes drying, as I said, to remove the moisture content, pelletization, so that it can be easily fed to the, or size reduction, so that it can be easily fed to the gasification unit. Then the other treatment methods to enhance the gasification efficiency, and there can be several. Now once this part is done, your fuel is ready. Okay. So what you need? You have to convey to the gasification unit. So if here is the gasification unit, you have to convey. So for that, you have to put a conveying belt. So third unit you will do is that here you will put a conveyor. Okay. Here you will put a conveyor. Okay. Now this conveyor can be like a screw conveyor, or it can be belt conveyor, or it can be any type of, for example, a screw feeder, lock hopper valve system, or it can be other custom design feeders. Okay. Now then after that it will enter to the gasification unit. Okay. So once it enters the gasification unit, it will require a controlled supply of air. So then what we do, let's say from here, so what we did initially, we collected the raw biomass, made a storage, then we developed a system that has the fuel preparation or pre-treatment unit, and then the conveyor belt. So this is, I would say here, conveyor or feeder. Okay. So we have the feeding system. Now after that it goes to gasifier. Okay. So in gasifier, the first thing you need for gasification is the air. Okay, and that should be controlled supply of the air. The reason is, if you remember, what is the difference between combustion and gasification? So combustion involves excess oxygen. That means whatever stoichiometric air is required, 10% higher than that. Okay, and it leads to complete oxidation. Whereas in gasification, what is needed is limited and controlled amount of oxygen. Okay. Therefore the air supply becomes very important. Now the air supply itself is a big unit. Okay. So this will have a compressor, this will have rotameters or flow meters, pressure controllers, and then air filtration units, because air you are sucking from the environment, so it also sucks the particulate matters and so many things. So this air compressor, so here I can say that the air compressor will have the filtration unit, pressure regulation, flow measurement, etc. Okay. Now this is important because flow meter will control the air supply according to the 30 to 40% of the stoichiometric ratio. And it is important if we have to control the composition and syngas, quality of the syngas. Okay. Similarly, it also prevent if I have limited supply 30 to 40%. Okay, it can be in some cases 20% as well, but 20% is a lower side, whereas the 40% is the higher side. So usually we stick here to the 30%. Okay, to prevent the complete combustion of the biomass. Okay, now uh, this is you can see, as I said, there is an air inlet which is connected to the gasifier, and this includes the airflow regulator. Now airflow regulator, as I said, the mass flow controller, it can be, or volumetric controller. What it does is that it controls the amount of air that enters into the gasification unit. Now when we can control between 30 to 40%, we know that partial oxidation will happen, and complete, there are less likely chances for the complete combustion, because you are not giving that much of oxygen and that much of air into it. Okay. Then also how much air is needed, that depends on the feedstock quality, and then the other parameters, for example, temperature, pressure, and the kind of syngas quality you require. Now, once this air enters into the gasifier, what happens? The partial oxidation of this happens. Now, this reaction, as I said earlier, that it produces a mixture of products, mainly combustible gases, COH2 and CH4, and non-combustible gases like tar and liquid byproducts, ash, char, etc. Plus, there will be nitrogen, there will be CO2 in addition. Okay. Now, if you see, I have now combustible gas. Let's say here it is coming. This will be at high temperature. Okay, and then I have the tar and liquid pipe products that I can take it as the condensate, and then I have ash and char, that is leftover solid. I can take it as the residue, but then all are at high temperature. So we have to design a system in such a way that we have to cool it. So for example, char and ash, which are being heavier, because of the gravity, they fall in the bottom. Okay, now when they fall in the bottom, what we do? We need a ash and char removal system at the bottom of the gasifier. Like I showed you during the household gasification, there is a ash scraper, ash pit, and a ash scraper that we use. Okay. Now, besides that, this is at high temperature, as I said. So when it is at high temperature, you need a cooling system, or here also you can put a heat exchanger or any kind of cooling system to handle the high temperature. Otherwise, it will be difficult. In addition to, you can say, this ash and char we can collect in a airtight container and allow to cool naturally, but then we'll be losing a lot of heat energy. And also what will happen in that case is, I can say that you will require large space, and because it is at high temperature, there is likely that it can catch fire as well. So there are several hazards that may be possible. Okay. Now, as I said that this condensate, ash, raw gas, all are high temperature. So it's not just the cooling that you require. Okay. You have to do a lot of things. For example, the condensate. The condensate will not have only the fuel, but it will also have water, tar, etc. So that has to be processed. That has to be separated. Okay. Now, for this, in fact, in the raw gas also, you will get some condensable vapor. So, firstly, let's focus that if we are getting the tar and the some liquid product here, okay, so we need a separate condensate line for it. Now, this collection system, as I said, the gas is coming at high temperature, so it will have a cooling mechanism. For example, water cooled heat exchanger or condenser, etc. Besides that, the cooling system will not only help to cool down the condensate, it also helps to condense the vapors. Okay, and then once it is condensed, if let's say we have tar and we have oil, both has different densities, so they can be separated by the gravity separation. Okay, now here the important part is that we should have a very effective control on the valves and mechanism, so that if we don't have a, what you can say, a good cooling system, then what will happen? The tar and the liquid vapors will remain in the vapor form, and then they will pass on to the another lines. And what will happen? They will start depositing where the temperature is low, and eventually the line will get blocked. So therefore, we ensure that the tar should not remain in the vapor form, and the cooling mechanism improve the efficiency of the tar removal. And also, as I said, it protects the downstream equipment from the fouling and the corrosion. Okay. Now, and the ash and char I have already told you. Again, we have cooling mechanism, and we can remove it using the ash scrubber. After once it is cool, we can use ash scrubber to remove it, and then we can use it for some other purposes depending on what is the composition of the ash. Okay. Now, coming back to the raw gas. So, the main product, as I said, combustible and non-combustible. So, we will have CO, H2, CH4, CO2. If it is air, I'm giving air, then I'll have also N2. I'll have some tar and some impurities as well. Okay. but collectively what we get is a hydrogen rich or CO2 rich syngas. Okay, now this syngas, as I said, it exits at very high temperature, and due to continuous gas flow the fine ash and char particles also get carried away. So what you can imagine, then what do we need? We need to have a cleaning system, right? So sometimes the uncondensed tar vapor also remain in the gas system. Okay. Then we need to have cooling system as well, so that it can condense the tar vapors, or if it has form tar is in the form of mist or a small particle, then we can use a separation system to separate them, or filtration system to separate them. So this is all for the today's class. See you in the next class. Thank you.